Saxon Algebra 1/2, lesson 106. Are you ready? I am. I'm pumped. We're going to talk some more about roots and exponents, a couple different kind of special case situations in the world of exponents that we're going to use forever and ever. So you'll have lots of opportunity for this to sink deeper into your brain. The first thing I want to talk about, I'm going to call it part A, is negative roots. And these can be a little tricky, but once you get the hang of them, it's not so bad. Okay, we know that the square root of 4 is 2. That's easy. Okay, what about this square root of negative square root of 4? Okay, well, we can do that using that same cover up the minus sign trick that we learned before, because that minus sign is not protected in any way, right? So I can cover it up. Square root of 4 is 2. And then I add the minus sign back on. That's perfectly fine. These are both right. Okay. Now, what happens if I put the minus sign inside? What this is saying is, think of two numbers exactly the same that multiply together to give me minus 4. And we're doing it twice, right? Because this is a square root. There's an invisible 2 there. So that means it's got to be two numbers. That it's the same number multiplied against itself, so multiplied twice. And the product is minus 4. There's no such beast. Because look, if we do 2 times 2, that's positive 4. And if we do negative 2 times negative 2, that again is positive 4. The only way to get negative 4 is to have one be positive and one be negative, but we're not allowed to do that. That's not how powers work, right? The number has to be exactly the same. So when the roots are even, I'm going to write this out and then I'll tell you what I mean. When taking an even numbered root, we can't use a negative number because as we see, every 2 negatives make a positive. So if we have a second root or a fourth root, right, then we'd have 4 negative signs, or a 6th root, we'd have 6 negative signs. All of them would pair off and we would never get a negative number. So we can't have negative pigs in our houses. Have I talked to you about pigs and pig houses yet? I don't think I have. That I won't say. I'll save that for later. So when we have an even numbered root, we can't use negative numbers. Now I will tell you this: in Algebra 2, we're going to learn the secret of how we can do it. But for now, we can't use a negative number. So I'm just going to write for now, because that will change later. But for now, no minuses if it's an even numbered root. Now let's take a look though. What if we have, and this is the first example, 106.1. John didn't show us the easy stuff in an example. I had to make that up myself. Okay, what about the third root of negative 64? Okay, so we see that this is an odd numbered root, so we should be okay, right? We can use a negative number if it's an odd numbered root. Let's forget about the minus sign for first. What number times itself 3 times will give us 64? Oh, well, that's 4 times 4 times 4, right? 4 times 4 is 16, and 16 times 4 is 64. Okay, in order to get the minuses, we're going to have to make that minus 4, aren't we? But when we add these 3 numbers together, we get the 64. We already talked about that. 1, 2, 3 minus signs. That means these 2 cancel out, but that is left. 1 minus sign is left, so the product is minus 64. So this one, the answer is just minus 4. Minus 4 is the third root of 64. And then let's do one more. Example 106.2. This time we're finding the fifth root of minus 32. Here's how I want your brain to read this. You see the minus sign inside the pig house. I call these pig houses. There's a 3 little pig story that goes with it, but I'm not going to confuse you with that now. We see a minus sign in a pig house and we go, holy smokes, wait, there's a rule about this. The rule has to do with even roots and odd roots. Even roots bad, odd roots good. 5 is an odd number. Okay, so we should be fine. So we're looking for a number multiplied by itself 5 times that gives us 32. Lucky for you guys, I play that game 2048. Oh, I always want to show you my phone when I'm talking to you, but I can't. It's just a simple little game, a little matching game on my phone, but it uses powers of 2, which is really fun. So 32, I know is a power of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 2 to the 5th power will get me to 32, but I can see I'm going to have to make it minus, right? These two cancel each other out. These two cancel each other out, but there is the minus sign that's left. So the 5th root of minus 32 is minus 2, and that is also correct. Okay? So even numbered roots, bad. Odd numbered roots, good, when you put a minus sign in the pig house. Okay, so that's negative roots. Now, before we talked about negative roots, now we're talking about negative exponents. And here's the weird thing about negative exponents. They live by their own set of rules. Okay, this has nothing to do with negative roots like we just did. They have it's a completely different rule. Completely different rule. It has nothing to do with what we just talked about, even though it's a minus sign. We have used minus signs in scientific notation. Like that, right? That tells us to make this number smaller. The negative exponents that we're using now are going to be completely different from this rule too. It's not like scientific notation. Those are indeed negative exponents, but we handle those differently too. So don't think about those. The very simple rule is that any time we take a base and we raise it to a negative exponent, this is how we simplify it. What in the world did I just do? This is how I think of it. This little minus sign is different than any other minus sign. This is actually a trapeze. You know how in circuses, you've seen them, you've heard of them, I'm sure. They don't really come around anymore. There's trapeze artists, right, that swing back and forth on those little swings. And they, one person will be swinging back and forth, like hanging by their knees over the bar, and then somebody else is swinging, and one person will flip off and the other person catches them. This is like that. This is the trapeze, and it flips the n and it makes it go down here. The x goes with it, right? Notice how it's x to the minus n becomes 1 over x to the n. That's what these little minus signs do. They flip the base and the exponent to the denominator. If you have it the opposite way, you've got your trapeze in the basement, dare I say, then guess what? It flips it up, right? So it can flip in either direction. And so there's a reciprocal nature of those, right? They turn our base into the reciprocal of the base. They turn the base into the reciprocal of the base. Oh, okay, well that's kind of weird. It always works this way. It works for letters and numbers. Sometimes with numbers we can simplify, and that's what our examples look like. Example 106.3. Okay, so we've got 1 over 4 to the minus 2. Oh, that looks like this, right? So we always flip the trapeze first. What I mean by that is don't worry about calculating 4 to the power of 2 yet. Flip the trapeze and then let's see what we've got. So I can see, okay, I'm going to flip it up, right? And it's going to become 4 squared. Now the trapeze is gone. By the way, once you flip it, the trapeze just disappears, right? That minus sign is gone. It's burned up in the flip, if you will, okay? And then we can simplify that. That's 16. Not so bad, right? You just flip it. It's fun. Okay, let's try a couple more. All right, this time, again, we have this form rather than this form, right? Because our original expression is a fraction with our special interesting parts in the denominator. This is an exponent. See how quickly it can start to look confusing? I'll try to be neater. Okay, again, don't worry about this minus sign or these parentheses. Just take care of the trapeze first. Remember that this minus sign has nothing to do with that minus sign. They don't cancel each other out. This minus sign on the exponent is just a trapeze. Students want to make it into something more than that. And it's not. It's just a trapeze. It doesn't cancel out. No, no, no. So we just rewrite this by flipping it. So we've got this style again. So this is going to become minus 2 to the 4th. See how I did that? I changed nothing. I just flipped it up. Okay, now we've burned up the trapeze. It's gone. Now we just have to simplify this. And that means we multiply minus 2 times itself 4 times. I'm just writing it out. You can do these in your head, but I just like to write them out so you know what you're doing for sure. 2 times 2 is 4, 8, 16. And then 1, 2, 3, 4, obviously, minus signs. So it's positive 16, which is the answer that we got for our last one. It's not necessary to put a plus sign here. We never have to indicate a positive answer. The lack of a minus sign tells me it's positive. But sometimes when I'm teaching, I like to do that so that you're crystal clear that it ended up being positive. Okay. But like on a test, I would not require you to put that. 106.5, ready? Poor Grace. Poor Grace we tried a different flea med for her this month and they didn't work. So we're going back to her old flea meds, but we can't do it until a month goes by. So she's kind of miserable this month with a lot of chomping. Okay, oh my gosh, there's even more, another minus sign. Okay, we can't cancel anything out. This is just a trapeze, so we're gonna flip it. We're still using, John's really into this style this time, isn't he? Right? Ah, the book just fell. Hang on. Hi, Grace, how are you? I balance my book on the arm of the couch next to the table where I'm working, and that works, I'd say about 98% of the time, but every now and then I get an avalanche. Okay, 106, here I am. Okay, so we still have another little section here. We have a couple more. Okay, so again, I'm following my same rule. This does not cancel out. This is just a trapeze. There's nothing to do except flip. Everything else in the problem stays the same. So this equals minus 3 squared. The only thing that changes is I flip it and that minus sign goes away. This minus is the same, this minus is the same. Makes sense? And this one gets burned off in the flip. All right, now we're ready to deal with this. I cover that up. That means this is minus 3 times minus 3. This much would be positive 9, but then I put that on it, so my final answer is negative 9. So tricky, right? These problems are not easy. They look deceptively simple, but holy smokes, there's a lot going on there, right? Okay, example 106 point. Oh, now on to the next idea before I tell you this one. Here is a very simple rule that I'm going to just tell you. John spends a fair amount of time trying to prove it to you. I don't think you care. Anytime you take a base and raise it to the 0 power, it's equal to 1. Anything, number or letter, raised to the 0 power is 1. That rule looks a lot like this rule, but they have a very different meaning, right? X raised to the 1 power, any base raised to the 1 power is just the base, right? You can take the number off or put it on, it doesn't matter. X to the 0 power is a whole different kettle of fish though. That the X blows up, or the number, letter, whatever it is, and it just turns into a 1. So let's do, this one's got 3 parts. Oh, John. It's such a cheater strategy. I'm just copying them all down. Okay, so here we're just practicing using this 0 exponent clause, and this is part C, 0 exponents. Let me just write that for organization's sake. All right, so let's try it in this scenario. Okay, 2 to the 0 power. Well, that looks just like that. That's 1. Negative 2 to the 0 power. Okay, let's use our rule. We can cover that up. It's not protected. So that becomes 1, but then there's a minus sign. So that becomes minus 1. This minus is not, it is protected, so I can't get to it. So this all just changes to positive 1. Okay? Just like with our other rules, if you can cover up the minus sign, cover it up, and then add it back on the end. If you can't cover it up, then it goes along for the ride and it gets demolished in the 0 powering that we do there. Okay, and then we have one more problem that is a little bit more involved that I think you're going to, this is 106.6. Sounds like a radio station. It's 106.5, isn't it? 106.7. Okay, that's our problem now. Simplify. Okay, this is what you'll see in the homework, I'm quite sure. Notice that I'm exaggerating the size of these. I'm double checking while you copy. Okay, so what do we do? Well, just like we've done before, we're using our product rule for exponents. We'll start with the base of x, and we're going to add the exponents on the x bases. So it's 2 minus 2. Oh, that changes to x to the 0, and that changes to 1. Oh, interesting. Okay, then let's try our y is 5 minus 2. Remember, we're adding these, but they have minus signs in front of them, so it looks like we're subtracting. Y to the 3rd. This turned into a y, so our answer we could write as 1 times y to the 3rd, but that's silly. We just write it as y to the 3rd. So that's our final answer. So when you get a base to go to the 0 power, then it just disappears. Poof, right? A 1 times anything, we don't need to write that. So it just disappears, all right? One other tiny little caveat that I just want to give to you. This rule implies that x is not equal to 0 because 0 to the 0 power is not a thing. Let's just say that. You just can't do that. And I'm not going to get into a big philosophical, theoretical description of why, but this can't be a 0. That doesn't work. All right? I don't think that comes up in your homework. Having a base turn into a 0 power and having it turn into a 1 and then disappear, that is a thing that you will see quite often. All right, guess what? That's the end of lesson 106. We're going to get lots and lots and lots and lots and lots and lots of chance to practice those lovely concepts, right? It was a negative exponent, what was the middle one? Oh, a negative, roots of negative numbers, a negative exponent, and 0 exponents. Those were our 3 topics. And now we're done with lesson 106. Halfway through the week. Good job. Goodbye.